Whether the PPT is visible, sir?
Yes, sir.
Yes, sir.
Okay, thank you. As already, sir, I have given my information about my research work and all the things. So I will start from directly my topic where we are going to discuss design studies of high power microwave source. And that particular source I will discuss. There are many sources of high power microwave, but today I will discuss about magnetically insulated line oscillator, that is called MILO. And this is mostly used in the defense applications. We will discuss how this is useful in the defense applications, how what are the features, how we can design this one. We will discuss this one. First, we will discuss the basic thing, that is what is high power microwave. Source, that is a device, but what is high power microwave? Which type of microwave we can call as a high power microwave? We know the range of microwave, but coming to the high power microwave, two things must be considered, that it must generate a power in gigawatt range, and it should be operating in the frequency range from 1 to 100 of gigahertz. It may be more than 100 gigahertz, but we are considering HPM mainly from 1 to 100 gigahertz. And that will produce a power of gigawatt power. And these HPM devices, they were mainly designed to disrupt, degrade, or destroy the target without damaging the infrastructure. Means we are, whenever there is I can say that is, if there is fight between two countries, earlier what happens, the people used to target with the help of missiles. Means that damage the infrastructure as well as that damage or hurt the people also. But the fight between two countries must not damage the people, must not hurt the people. Okay, they are having their things with that is, they can destroy their another infrastructure, that is called electronic infrastructure. In that way, we can generate this HPM for destroying the target, but not hurting the or damaging the infrastructure or hurting the people. And that thing, it is achieved by radiating a power of more than 1 gigawatt. 0.5 gigawatt also it is helpful, but I can say that if it is a power of more than 1 gigawatt, then it is more impactful for damaging the electronic equipment or targeting any enemies, that is for anti-drone system also. Recently we have seen I hope it's what in May 2025 during the Operation Sindhu, when Pakistan attacked India through the drones. Okay, in that, at that moment we were able to neutralize their drone. And that thing we were able to neutralize with the help of HPM devices. HPM devices can perform very well for neutralizing anti-drone system, for targeting the electronic equipment of any enemy particles. That is, if it is, I can say, if we are targeting their radar system, we are targeting their flights, we can damage their electronic equipment with HPM devices. Now, there are different HPM sources. Basically, these are relativistic magnetron, relativistic klystron, virtual cathode oscillator, which we call Virkacher, a relatron, and magnetically insulated line oscillator. And basically my research work and my work is mainly on the magnetically insulated line oscillator, because it is having some beautiful feature which is very helpful in many ways. Due to his attractive feature, it was I have chosen this magnetically insulated line oscillator. And this was I have worked for this magnetically insulated line oscillator for DRDO project also. Okay, that DRDO project data I can't reveal, that is very much confidential. Okay, but other thing apart from the DRDO work, whatever I have done, I will try to make it clear to you. What is the application of this high power microwave source? First one we discussed, that is non-lethal HPM weapon. What is the meaning of this non-lethal? Then non-lethal means those weapon which does not impact the human being. It is not going to harm the human being. Those weapons are called non-lethal weapon. Now coming to electronic warfare, we can say that these HPM devices are used to disrupt the electron. If it is electronic war, means I can say I am going to damage the electronic circuit or electronic things of the other country. For that purpose, our HPM devices are used. Okay. Now coming to directed energy weapons. We know that conventional weapon, what is the things with the conventional weapon? That conventional weapon carries a magazine. Okay, but here the directed energy weapons, they are operated with high power, high voltage. Okay, high voltage, they are operated with high voltage. But this magazine, if it is a conventional weapon, they are dependent on the magazines. Okay, and if there is a war, then I can say in the war it is not possible to extend the magazine if it is over. But here we can supply uninterrupted power for the directed energy weapons. Okay, now what is directed energy weapon? Those weapon which carries energy or which carries power or which radiates, that is called directed energy weapons. It is not directing, or it is not uh, mm, injecting the materials. It is not injecting the nuclear material or anything. It is radiating the power. Those things are called, those weapons are called directed energy weapons. Means these are the application of high power microwave. And other application is in the radar imaging. Now I will show you few directed energy weapons application. That is, see, all these are directed energy weapons which are used in the military applications. You can see here a large truck mounted. It is mounted with high power source. Okay. Other, that is here also you can see there is a one high power. These all are here at the top. Also you can see that HPM is radiating high power microwave and it is targeting the aircrafts. Okay, this can be mounted on a small truck also, and it can radiate in any directions. Okay, now coming to directed energy weapon, they are basically classified into three categories. This can be a laser directed energy weapons. It can be a HPM directed energy weapons. It can be a particle beam directed energy weapons. Okay, but basically today I will discuss about HPM weapon, because we are not focusing much on laser directed energy weapon or particle directed energy weapon, because HPM directed energy weapon have some advantage. What are those advantages? First advantage is that HPM directed weapon it is not having any problem during radiation or propagation in the atmosphere. But this laser and particle beams suffers from the atmospheric losses. Okay, that's why we are we are mainly focused on the HPM directed energy weapon. And one more beautiful thing is of the HPM directed energy weapon is that laser and this particle are very pinpoint. Pinpoint means I can say very precise targeting is required for if I'm using a laser directed energy weapon, very precise targeting is required. If I'm using a particle beam directed energy weapon, in that case also very precise targeting is required. Okay, means I can say they are very pinpoint targeting for laser and particle. But for HPM, their spot size is large enough, means there no precise targeting is required for HPM directed energy weapon. Okay, two basic thing is the beauty of HPM weapons, that is they does not require precise targeting, and second thing is that they does not suffer the atmospheric losses. Okay, means they can easily travel through atmospheric all the atmospheric layers. Okay, that's why this HPM's directed energy weapons we are preferring nowadays. Now coming to the main topic, that is magnetically insulated line oscillator. Okay, what is magnetically insulated line oscillator? Why we are calling it is a magnetically insulated line oscillator? What is the feature of this magnetically insulated line oscillator? What is the configuration, how it is designed? What are the component of this magnetically insulated line oscillator? Okay, or then we will discuss how we can design this magnetically insulated line oscillator and how we can visualize the result from the simulations. Okay, if I will be able to show here the simulation, if I will be able to share my simulation screen, then also I will show how to design it in a CST. Basically, I am working on the CST simulation tool. Then I will show you how to design a particular device. Just a unit cell I will discuss with you people, because entire design of the entire magnetically insulated line oscillator, it is too complex. It requires, it will take more time to discuss that simulation process of this magnetically.
Hello.
Yes. Someone mic is on. If it is possible, kindly mute that one. Now, coming to my magnetically insulated line oscillator, it works on the principle of self-magnetic insulation. Okay, so it does not require external magnetic field for focusing the of electron beam. Whenever a high power microwave device is designed, in that case there are some there is one basic component is required, that is cathode, and another is anode. And cathode is the source of electron beam. Now in the case of high power microwave HPM source, we need the focusing of the electron beam for interaction, with the EM wave. Here in magnetically insulated line oscillator, what is happening, that the kinetic energy of the electrons beam are converted into the radiating, that is RF wave. Okay, high power microwave, that kinetic energy is converted into high power microwave. The kinetic energy of the electron beams interact with the fundamental mode of the slow wave structure, and that interaction, within that interaction, the energy of the electron beam is transferred to the RF wave, and that wave propagate with carrying high power along with that wave. Okay, I will discuss that part, how this self magnetic insulation occurs. And this is cross field device. Cross field device means, here the meaning of the cross field device is that electric field and magnetic field and the direction of propagation all are perpendicular to each other. Those type of devices are called cross field device. And this is a slow wave device. I will discuss what is the meaning of slow wave and what is the fast wave. Okay. It operates mode of operation is TM mode, that is transverse magnetic mode, and pi mode of operation. Also, I will discuss what is the meaning of pi mode operation. Later on in the next slides, upcoming slide, it is discussed about what is the pi mode. It is there, and what is the slow wave devices. Okay. This is the schematic of magnetically insulated line oscillator. You can see here a cathode. This is completely a cylindrical structure. Don't be confused that it is represented with the line. With a line means it is just a line or it is a wire. It is a cylindrical, hollow cylindrical structure. That hollow cylindrical structure works as a anode. Okay. This Milo consists of two cylindrical structure. One is this cathode and another is anode. Okay. And this anode consists of periodically spaced disc. This disc, you can see that is 1, 2, 3, 4, 5, 6 discs are there. Okay. It can be more also. That is not a fix that it can be 6 or 5. But here for the single frequency magnetically insulated line oscillator, here six discs are placed. First 2 discs are choke cavity. I will discuss what is the meaning of choke cavity. And these 3 discs are the interaction cavity. Means interaction cavity, here the interaction between the electron beam and the RF wave occurs. Okay. And last one is the extractor disc, which is used to extract the standing wave power here. Okay. Now the components, just discussing the component of this magnetically insulated line oscillator. These components are cathode, interaction cavities, choke cavities, extractor and stub. Okay. Now, what is the cathode? For any high power microwave source, we need a source which can generate electrons, plasma, which can generate electron beam. And that source is our cathode. Okay. Now to confine or to generate the fundamental EM wave and to confine this cathode, one magnetic field is required. Okay. And for this interaction, some interaction structures are required. Now here the beauty of this magnetically insulated line oscillator is that it is a self-magnetic insulation. There is no need of external magnetic field for focus. Now how this self-magnetic is induced here, whenever I will discuss this whenever a high voltage between cathode and anode is applied. Okay. Whenever a potential difference between cathode and anode is created, in that case, the resulting electric field creates a high plasma density near the cathode. Means these electrons are explosively emitted from the cathode surface and create a plasma, and that plasma is the source of electron. Okay. When a high voltage, high potential difference is created between cathode and anode, and that potential difference, voltage required for that potential difference is more than 400 or 500 kilovolt. that much potential difference is created. Okay, I have applied worked for 500 kilovolt. Okay, means I have given a supply. I have created a potential difference between cathode and anode. That potential difference is of 500 kilovolt. If a 500 kilovolt potential difference is created between this cathode and anode, this anode is at the top of anode. It is a that is velvet, and from that velvet, uh, electrons are expositely emitted, and that electrons try to reach this anode. Okay, when they are in the next structure, I think I'm having 1 minute. Here, okay, I will discuss that one in the next day. Whenever these electrons are emitted from the cathode, they are trying to reach the anode. Okay, but if they will reach the anode, there will be a electrical breakdown. Okay, and device will cease to operate. For that case, we need some external magnetic field. But what happens here, these electrons which are emitted from the cathode, they creates a path with this stub. Here stub is connected, you can see in the picture, one stub is connected, and that create a path of current. Okay, and if the current flows in this from this stub towards this left side of this anode, in that case, if there is a current flow, you know that if you are having a current flowing wire, what happens? A magnetic field is generated, and that magnetic field you can, direction of that magnetic field you can decide with the right hand thumb rule. I hope you people are aware about that right hand thumb rule. And the same thing is happening here. Whenever these electrons are emitted from the cathode, they are the source of the current. They are generating the current, and that current is forming a path with this feedback stub. Okay, and whenever there is current flow in the anode, they are creating a magnetic field. That is called self-generated magnetic field. Okay, and that self-generated magnetic field is due to the current which is flowing in the anode. Okay, and that self-generated magnetic field, now whatever the electron which you are trying to reach the anode, that electrons will now be prevented from reaching the anode. Okay, now here there are three components, that is, we can say electric field is there. Why the electric field is there? Since we have created a potential difference between cathode and anode, that is creating a electric field. Now here it is a magnetic field also is there. Okay, that magnetic field, it is generated due to this current flowing through the anode. Now if you know this, just a few things about the basic. If we know the direction of electric field and if we know the direction of magnetic field, we can calculate the direction of propagation, means in which direction this will propagate. Okay, so since here electric field is in the radial direction, and this direction of this magnetic field, it is in the phi direction. It is, if it is a cylindrical structure, you know what are the coordinate of the cylindrical system. That is, I can say that is radial rho phi z. If you know, that is rho phi z. If I know that is electric field in the rho direction, magnetic field in the phi direction, then the propagation direction will be our z direction. Means along the axis. Now, whatever the electron beam, they are prevented from reaching the anode, and they started moving towards the moving parallel to the anode. Okay, and they will move toward the collector axis. Okay. Now, just one very basic thing, if is that the phase velocity. The phase velocity of the EM wave in cylindrical waveguide, it is more than the speed of light. Okay. If you people know, otherwise, if you are not knowing, also you must note this point that the phase velocity of EM wave, it is greater than the speed of light. Okay, in the cylindrical waveguide, I am discussing about the cylindrical waveguide because this complete Milo is a cylindrical structure. Okay, now if it is greater than this phase velocity is greater than the speed of light, then there is of no meaning because our electron beam is not traveling at that fast speed. Okay, and the speed of electron beam is slow, and the wave which is generated here inside this cavity, it is traveling with a very fast speed compared to the speed of light. In that case, there will be no interaction. When interaction occurs, if you are if two people are going, and if one is going very fast and another is going very slow, will be able to interact with each other? No, because one person will cross another very fast. Okay, RF interaction is required, then only the kinetic energy of the electron beam will be transferred to the RF wave. Okay, and for those interactions, these discs are applied here, this interaction disc. And why these discs are called slow wave disc, slow wave structure? Because they are reducing the speed of the phase velocity. They are reducing the phase velocity. Okay, how they are reducing? Since see, if they will they will travel the zigzag direction. Okay, they will go through this zig directly. They are not moving. There is an obstacle now. Okay, means for reaching from starting to the end, now they will take more time. Or distance velocity, I can say that is displacement from starting to the end is same, but they are now disturbed. They are disturbed with the slow wave disk. If they are disturbed, they are taking more time. If they are taking more time, then their velocity is reduced. Okay, that velocity, if the velocity of the RF wave becomes equal to the drift velocity of the electron beam, in that case they will interact with each other. Okay, they will interact with each other. If they will interact with each other, the kinetic energy of this electron beam will be transferred to the RF wave. Okay, now I will, in the upcoming slides, we will discuss how this see, you can see this disk are periodically spaced. Means what is the period, at what period we have to keep this disk? Randomly I can't keep. No, they are kept at some distance, they are having some thickness, they are having some depth. All these things, parameters are used. See, depth is mainly helpful in deciding the frequency of operation, and this periodic structure means at what period it should be kept. They are very much important in deciding the uh, phase velocity and drift velocity. Okay, means we have to synchronize them. If there is a interaction between them, then only they can transfer their energy. For that reason, that period decide that period plays a vital role for synchronization of drift velocity beam and wave. Okay, drift velocity of the electron beam and the phase velocity of the RF wave. Okay, in the upcoming slide, I will discuss what is the formulas for to calculate that one. Okay, now what is the attractive feature of this magnetically insulated line oscillator? First attractive feature is that it can generate a power of gigawatt level. Why gigawatt level? Why we are bothering about gigawatt power level? Because this gigawatt power level can be used for high power microwave weapons or directed energy weapons. Okay, that means our Milo is successful in generating gigawatt level of power. Now, another thing is that both insulating magnetic field and accelerating voltage are produced by the same source. Means who is producing the magnetic field here? How the magnetic field is produced here? We are applying the voltage between anode and cathode. That applied voltage is resulting in the high electric field. That electric field is resulting in the explosive emission of the electron. That electron is now creating the current, generating the current, and that current is resulting into the formation of insulating magnetic field. Means the source which we are applying, the same source, it is applied for the electron beam generation, and the same source is applied useful for the insulating magnetic field. Okay, that is, there is no much tuning is required between the applied voltage for electron beam and for the insulating magnetic field. Okay, that's why it will operate at high voltage. It can operate at high voltage because the tuning is not required now. If there are two different voltages required for creating a magnetic field, if one is another voltage is required for creating magnetic field and another voltage for generation of electron beam, then there is tuning is required between them. Okay, but here no tuning is required due to single source is generating both the things. Okay, next one is external magnetic field is not required. If external magnetic field, if you whatever the external magnetic field required for focusing the electron beam, it is of very large structure. Okay, very large magnets are required for focusing if we are using external magnetic field. But the beauty of the magnetically insulated line oscillator is that no external magnetic field is required, and due to that our device becomes much compact. Our device become much compact to other, compared to other devices. Compared to other devices which need external magnetic field, the device which does not need external magnetic field, which is generating self-generated magnetic field, now that device definitely will be compact compared to other which is required external magnetic field. Now, this is the beauty of my, that is, it is very compact device. Another is that frequency tuning is very easy. The frequency tuning is by knowing very easy because this frequency is completely decided by the depth of the disc. If we are tuning the frequency, if I will change the depth of the disc, the frequency will change. That's why the frequency tuning is very easy here. And it is very stable device, means once it is designed, it can operate for number of repetition. And just I have kept few models of this magnetic insulated line oscillator. Just I have shown you the schematic. Now this is the 3D simulation model. Okay, this one is the 3D simulation model. Earlier in previous slide we have seen the schematic. Okay, now this one you can see both are the cylindrical structure. Now this one is inner cathode and outer is the anode, and in the outer structure there is periodically spaced discs are there, and these discs are kept at a fixed period. And okay, at the last this one is the beam collector. At the last it was the beam collector, and this one is the stub. The stub we have seen that is which is connected to the beam collector. Okay, this one is the both these figures are 3D simulation model. One more model I have kept, that is I have designed this one model. This is not having I can say this is not the complete structure. It is not having the beam collector, just it is the interaction structure. Okay, Just to visualize, for more visualization, I have kept this structure so that you can visualize how it is internally. Just seeing the schematic, you can't visualize how the internal structure of the Milo is. Okay, that's why I kept the 3D structure, and these two are the simulation model, and next one is the design with the CATIA. Coming to the operation mechanism, how this Milo operates. Okay. Uh, I hope you people are getting the things. So I am continuing this operation, how it operates. Just in the previous slides also I discussed, but here I will discuss little bit with the help of other figures. Okay. See here, the main basic is that we have to create a high potential difference. Na? Just I have discussed that Milo is a two conductor system. Okay, a smooth one. A smooth one inner conductor is the cathode. Anode is the outer conductor which consists of periodically spaced cavities. I hope you people are clear with the cathode and anode. The smooth inner structure, inner cylinder is the cathode, and the structure which is having periodically spaced cavities, and the outer structure is the anode. Now, whenever this supply, here you can say there is a supply in between anode and cathode. Okay, whenever a high voltage, high potential difference is created between anode and cathode, means we have to supply in kilovolt to megavolt also. Okay, then the large electric field generated will create the plasma at the layer of the cathode. I hope it is clear how this how these electrons are created, how these electrons are expressly emitted. How electrons are emitted from this cathode? By applying a voltage, high voltage in between cathode and anode. If you are applying, by creating a high potential difference, and that high potential difference is leading to high electric field, and that high electric field is creating a plasma layer on the surface of cathode through the explosive emission. There are different type of emissions. Okay, thermionic emission, explosive emission. Okay, means some emission, thermionic emission, they are dependent on the temperature. If the temperature exceeds some level, then the electrons are emitted. That type of emission is called thermionic emission. Okay, in the explosive emission, here the electric field, means electric field is beyond the threshold electric field. If the electric field is beyond the threshold electric field, that will create the emission of the electron from the surface of the cathode. Okay. Now, whenever this voltage is sufficiently high only, okay, then the force associated with the self-generated magnetic field will be strong enough to bend the electron trajectories. Okay, just I will show here two diagrams. Whatever the statement I have given, for that statement I have kept the two diagrams. Above diagram, I can say that the potential difference which was created, it is not enough to generate the self-generated magnetic field. It is generating the magnetic field, but it is not that much which is creating the magnetic insulation. Okay, means if you are supplying the voltage, that voltage is generating the current, and that current is leading to the magnetic field. If that voltage is not sufficient enough, then the current will be less than the critical current. Now, what is the critical current? Critical current is the minimum current which is required for the magnetic insulation. We define that current as a critical current. Okay. If the current in the device is less than the critical current, then these electrons emitted from the cathode will reach the anode. They are not insulated now. Okay. Now, if the voltage is sufficient enough, okay, then it will generate the sufficient current. And if the current is greater than the critical current, then sufficient magnetic field will be generated, and these electrons are prohibited from reaching the anode. You can see the two structure. Above structure, the electrons emitted from the cathode, they are reaching the anode. It is represented by the arrow sign. Now, here in the lower diagram, when the current is greater than the critical current, the electrons emitted from the cathode, they are not reaching the anode. They are bent. They are bent. Okay. The magnetic field is enough to bend the electron trajectories. And now they are bent such that they move parallel to the anode structure. Okay, they started moving parallel to the anode structure. If they are moving drift, means I can say they are drifting parallel to the anode structure, and with the whatever the velocity with which they are drifting, that particular velocity is called a drift velocity of the electron beam. Drift velocity of the electron beam. Okay. I hope you know the relation between electric field and the drift velocity. Okay. That drift velocity is due to this electric field. This is creating all the things, and this magnetic field is bending this electron trajectory. Now they are traveling, moving parallel to the anode structure, and with whatever the velocity with which it is moving forward, that velocity is called drift velocity. Okay. Now these electrons are initiating, they are exciting the fundamental mode inside the structure. This is the same electron, they are exciting the fundamental mode inside the structure. Okay. And that fundamental wave, whatever is generated, they are having some phase velocity. And in case of, if it is a smooth, here I have shown that I have placed periodic disk. If there is no periodic disk, if the anode is also smooth, in that case, the phase velocity of the wave which is generated, it will be greater than the speed of light. Okay. Now to reduce that phase velocity, the disks are placed. Okay. Now if the disks are placed, one equation will be there. That is called the equilibrium equation. That is Vp, the phase velocity of the RF wave will be equal to the drift velocity of the electron beam. If that synchronism condition is achieved, means phase velocity is equal to the beam velocity, in that case, here these electron beams are interacting, means they are transferring their energy in the form of punch. Okay. This spoke formation, this is called the spoke formation, and in the form of punch, they are transferring their energy to the RF wave. Okay, this one is the basic diagram which is drawn to understand what is the direction of magnetic field, what is the direction of anode current, what is the direction of electron current, what is the direction of cathode current. Okay, you can see when here high transmission voltage is applied. Okay, E naught R is represented in the figure, that is the electric field direction. Okay, here this dotted line circular, it is the magnetic field direction. Okay, it is in the phi direction. Okay, and this will be your anode current direction. This is the basic diagram which is representing the current direction and electric field and magnetic field direction in the device. Okay, If you wish to visualize the direction of propagation and all the things, it will be helpful. The electron field, sorry, electric field direction and this magnetic field direction. Then what will be the direction of propagation? Okay, this direct and these directions will be helpful to calculate the direction of propagation. For analyzing that one, just for analyzing that one, I have kept that one. Yes. Now, whenever this is the simulation model I have kept for you people. See, figure number 1. Figure number A, it is represented by A here. Figure number A, you can see whatever the electron beam, blue one is the electron beam. Na? Whatever the electron beam emitted from the cathode, they are reaching the anode. You can see it is reaching up to the anode. Okay, figure number A. Why they are reaching? Because in the starting, when just we have started, we have the supply. Whenever we started the supply, what was happening? The current was not enough. The current was not enough to generate sufficient magnetic field to confine them. That's why the electron, whatever emitted, this device have been operated for 100 nanoseconds. This device have been operated for nanosecond, and figure A is at 2 or 3 nanosecond. Figure A, when it was 3 nanosecond, after the supply, then this current was not enough. In that case, all the electrons emitted from the cathode, they were reaching the anode. Now you see the figure B. There are 3 phases of operation. There are 3 phases of operation. Figure A is pre-oscillation phase. 3 phases are pre-oscillation phase, linear phase, and non-linear phase. Okay. Pre-oscillation phase. Pre-oscillation phase is the phase where the current generated within the device is less than the critical current which is required to insulate the electron. Okay, that is pre-oscillation phase. In the pre-oscillation phase, whatever the electrons emitted, they are reaching the anode. They are not confined now. Now you can see the figure B. Figure B. In the figure B, it is just very the current is very close to the critical current. Okay, it is nearly equal to the critical current required for insulating. In that case, you can see all these electrons emitted from the cathode, they are not reaching the anode now. They are moving axially. They are moving axially towards this collector. They are not reaching the anode now. They are confined now. They are confined near the tip of the disc. That is the linear phase. Diagram figure number B. And all the figure number from C to F. The C to F, that is the non-linear phase. Non-linear phase, that phase is the phase where energy is transferred from electron beam to the RF phase. Okay, this phase occurs, this from figure C to F, this phase occurs when the phase velocity and drift velocity of the electron beams are equal, nearly equal. If those are nearly equal, in that case, the electron beam, the energy of the electron beam are transferred to the RF phase, and that is the non-linear phase. In the form of bunch, you can see they are in the form of bunch. They are transferring their energy. This is called a spoke formation within the device. Okay, they are transferring their energy. This is the 3 phase of the operation of the magnetically insulated line oscillator. Okay, this one basically, this structure is dual band magnetically insulated line oscillator. Okay, this is the dual band. There's also there is single band. I have worked for both dual band and single band. This structure is basically for dual band. Okay, that's why you can see one at starting it is the depth is more, and at the last part the depth is less. The depth of the disc only decide the frequency. Here we have created 2 different depth, means 2 different frequency. One is in the one is in the S band, another is in the X band. Okay, two band, they are operating at two different bands. Oh, okay. This is the design procedure that if we are okay, this we will discuss it. Suppose we are going to design any Milo. First thing is that first we have to decide. I have to design a Milo of what frequency? What is the frequency? What should be the frequency of operation of that device? Okay, we have to choose first at which frequency I wish to operate my Milo. Okay, what is our frequency? What is our requirement? That should be decided first. That is the first criteria. Okay, now then we will calculate for according to our supply voltage, we will calculate the relativistic mass factor, critical current, anode current, and cathode current. For all this, there is a formula, okay, to calculate all these parameters, that is relativistic mass factor, critical current, anode current, and cathode current, which will be required for the design procedure. Okay, first we have to decide the frequency, then as per our supply voltage, this formula, this relativistic mass factor, critical current, anode current, and cathode current, all these are dependent on the voltage supply. Okay, those corresponding to our supply voltage, these all the parameters are calculated. Now we have to calculate this L, means period, at which period it should be kept. Okay, what should be the period of at which the disc are kept. Okay, another thing, for a standard cathode radius, then in the whatever the cathode available in the market. Okay, suppose it is cathode is of 25 mm, radius of the cathode is 25 mm. Now corresponding to the cathode radius, I have to calculate the inner radius of the disc. Okay, that is Ri. Okay, cathode radius here I have represented with Rc, and inner radius of the disc it is represented with Ri. That there is a relation, that is Ri is equal to 1.6 times of Rc, and that was calculated with the help of empirical formula. That is a empirical formula that was decided after n number of experiment, that if the Ri is equal to 1.6 times the Rc, then there will be a sufficient beam wave interaction or significant beam wave interaction will occur. Okay, nearly we used to keep Ri is equal to 1.6 times of Rc. Okay, now depending on the frequency of operation, this D1 means depth of the disc, thickness of the disc, and these parameters are calculated. Okay, now after calculating all these parameters for our frequency of operation, for fixed frequency of operation and fixed operating voltage, these parameters are first calculated, and then these parameters are modeled in CST. With the help of this parameter, we use to model a unit cell. We are not going to model the entire structure, because if we model the entire structure and at the end if we are not getting the required frequency, that is wastage. Okay, that's why we used to just model a unit cell, just unit of cell of that complete structure, and whatever the unit cell, if it is showing the same properties which we require, then we can move to full design of the Milo. Okay, if it is we are not getting the desired frequency, then we used to optimize L1 and L2, means we used to optimize this parameter, that is period. L here is the period, T is the thickness of the disc. We used to optimize. Okay, if after optimization we are getting our desired frequency, then okay, we will start the simulation. We will start the complete design and we will start the simulation. This is the basic design procedure. few equations are there which is important for the design. That first equation is Ri by Rc is equal to 1.6. Rc is the radius of cathode and Ri the inner radius of the SWS disk. Okay, and RC is the standard. That is you people may be bothered about how we are calculating the RC. We are not calculating the RC depending on what dimension cathode is available in the market. Depending on that dimension, we use to calculate RI. Okay, basically, but standard we have kept 25 mm. 25 mm standard cathode is available in the market. Corresponding to that one, we have calculated RI. Okay. Now, corresponding to the frequency, don't be confused that, sir, you are writing the frequency here and you are giving the formula. We are not calculating. First, we are deciding the frequency, and that formula will relate us to calculate the period and thickness. This is the formula for frequency. But here we have to do the reverse engineering. Here we have to do the reverse engineering, means with that formula we have to calculate what will be the period at which the discs are kept and what will be the thickness of the disc. That formula will be helpful to calculate. This all the things that C dash, C, these all are this F naught. In F naught it is 1 upon 2 pi under root L dash C. This all this parameter, that's L dash, C, C dash, these are dependent on period of the at which the disc are kept and thickness of the disc. Okay, and the depth of the disc. All these things are dependent on those parameters. Means here with the reverse engineering, we are calculating those parameters. First, we are deciding our frequency, then we are calculating the dimension. We are not first deciding the dimension and calculating the frequency. Then it will be not helpful for us to operate on the desired frequency. Okay. First thing is that we are fixing our desired frequency, and by doing the reverse engineering, we are calculating those parameters which will give this particular frequency of operation. Okay. With that, equation number 2, we will calculate all these parameters D, L, and T. Here you will see, you can see that these L, D, L, T are not mentioned here. If I will mention that one, it is very large formula. It will be very confusing for you people. But all these parameters C dash, C, L dash, all are this dependent on D, L, and T. Okay. That formula is not kept here. If you wish, I can refer a particular paper where all these formulas are given, and by that reverse engineering, you can calculate D, depth of the disc, L, if it period of the disc, T is the thickness of the disc. Okay. Now, the main objective is to synchronize between the electron beam and the RF wave. Okay. Now that synchronism will be established when our VD and VP are equal. What is VD? VD is the drift velocity of the electron beam and VP is the phase velocity of the RF wave. If both are equal, then only there is a transfer of kinetic energy of the electron beam to the RF wave. Then only we can say we are generating the high power microwave. Otherwise, we are not able to generate the high power microwave. Okay. And you can see in the formula of phase velocity, it is 2LF, that is where L is the period or periodicity at which the discs are kept. With this formula, that if you equate VD and VP, that VD drift velocity, it is directly related to applied voltage and the anode current and the RI and RC value. Okay. We can easily calculate the VD if we know the applied voltage, if we are able to calculate the anode current, if we have our RC value, that is radius of cathode, if we are having the inner radius of the SWS, this will be able to calculate this VD. Okay. But coming to VP, we have to equate the VD equal to VP by keeping 2LF, and from there I will calculate L also. Okay. We have to equate those. We have to keep our L value such that this VD and VP are equal. In that case only, there will be interaction between beam and RF wave. Then only in the last line you can see the beam wave interaction mechanism start when the electron axial drift velocity is equal to the RF phase velocity. Okay. For this to occur, our main target is the interaction, the interaction of electron beam and RF wave. If the interaction is much, there is better interaction, in that case there will be more in power will be generated. If there is weak interaction, the power will be very less and the efficiency will be very poor. Okay, that's why it is very important to synchronize these two, VD and BP, and for that synchronization is achieved with the help of this periodicity at which we are keeping the disk. These are the basic formula for the calculation of these things. If it will require, I will share the slides also, and I will refer the papers also, no problem. Now, yes, just this one is the basic unit cell. See here, earlier I have shown you the complete design. Earlier I have shown you the complete design of the Milo, but here I am not showing the complete design. This one in the unit cell. This one is the unit cell, means it is of the L. It is having the periodicity L. It is designed R radius of cathode. It is having Ri inner radius, and it is having the outer radius of the anode. All the things are there, but we are not designing the complete structure. This is the unit cell which we design in the CST, and according to that unit cell, in the eigenmode simulation, we have to keep that we are doing the periodic. Okay, this is the periodic structure. That's why we are able to design a unit cell and retrieve all the properties. If it is not a periodic structure, we will not be able to design a unit cell, and we will not be able to retrieve the properties of the entire structure. Since that structure is periodic, in that case, we are able to design a unit cell and we will be able to retrieve all the properties of the entire structure. Okay, means at which frequency it will operate, what will be the axial electric field, what will be the radial electric field, all the properties we will be able to calculate. Okay, and after the simulation of this unit cell, for n number of modes, we got this one. Okay, and we have finalized that lower mode. It is the lower mode of operation is the mode of operation. Okay, here I have kept mode 1, mode 2, mode 3, mode 4, and mode 5. At lower mode only, here the interaction occurs. That is the lower mode we have kept for. If they are very close, in that case, I can say their mode competition also occur. Then one term you must know, what is mode competition. Mode competition is like if two frequencies are very close, then some of the power will be distributed to the second frequency, undesired frequency also. That is called the mode competition. Okay. Now with the unit cell, we used to retrieve our dispersion curve, and at 180 degree, we check what is the frequency. Just I have mentioned pi mode. Pi mode, in the pi mode, we have to check the frequency at 180 degree. Okay. If at 180 degree, whatever the frequency, that will be the operating frequency of our device. It is not 100% confirmed that whatever the operation frequency, it will be generated by Milo at the end also. There will be a slight variation may occur. Okay, exact it is not you can get, but slight variation we can accept, no problem. Similarly, this is for X band, that one is for S band. Okay. Now, after after getting the data of this eigenmode simulation, then we design the full model. That one I'm going to previous slide. This one is the full model. Okay. This 3D model, these are the full model of the Milo. Okay. But here I have kept that just unit cell. After getting the data from the unit cell, then if we are satisfied, okay, our operating frequency is whatever we have desired. If it is okay, then we will design the full model, and then we will simulate the particle in with the help of particle in cell simulation. Okay, and at the end, after the simulation, we were able to achieve 3.6 gigawatt of maximum power. And you can see here, this one is short time Fourier transform, and you can check that you can see here two frequencies. One frequency has 3.4 gigahertz and another at 10 gigahertz. It is generated. It is short time Fourier transform means the advancement, I can say it is the temporal advancement of the frequency with respect to time. Means I can say for the entire duration when it was generated, was generated nearly at 10 nanosecond, and for the entire 100 nanosecond, it was the device was able to generate that two frequencies. That is the dual band Milo. Okay, it was able to generate the two frequency of 3.4 gigahertz and another one of 10 gigahertz with a maximum peak power of 3.6 gigawatt, and that will be able to disrupt or destroy the electronic circuitry, or that will be used for anti-drone system. That is we are able to generate the high power microwave with that device. Okay. Now these are my publications. First one is my granted patent, and all these are the publications. Okay, these are the international journal in the most all maximum are all in reputed journals. IEEE transaction on electron devices, IEEE transaction on plasma science. Okay, and recently I have started working in the field of absorbers, metasurface absorber, that was published in Journal of Optical Society of America. Okay, and these are the conferences which was submitted by my student, and it was completed by my BTech student. Okay. If, thank you for the session. If you are having any query, you can raise your query.
Now, students, if you have any query, please clear it from Dr. Singh.
And one more thing, if you are having any query at later time also, you can ping me my mail ID with sir also, and I can share my mail ID also. My mail ID is mohit4689@gmail.com. And if you really wish to work in this area also, you can ping me. Okay, just you can message me. I will reply through the mail also, no problem.
Okay, thank you, sir.
Thank you, sir. If a students you are having any query, you can raise.
No problem. Students, if you have any query, please ask.
Yes, sir. Sir, I have one question.
Yes.
सर, ये जो आप टॉपिक बोले थे मैग्नेटिक इंसुलेशन, सर इसका क्या रोल है सर?
मैग्नेटिकली इंसुलेटेड लाइन ऑसिलेटर।
यस सर।
इसका ये रोल है, ये यूज होता है डिफेंस एप्लीकेशन के लिए। ठीक है, सपोज कोई भी अगर दो कंट्रीज में वार होता है,
yes,
तो हमारा जैसे भी रिसेंटली हमने डिस्कस किया जस्ट आपको कि मई में जब इंडिया पाकिस्तान में जब थोड़ा सा ऐसा हुआ था, जब ऑपरेशन सिंदूर के समय, तो दे वर अटैकिंग थ्रू द ड्रोन्स। ओके,
यस सर।
नाउ these high power weapons, if we are radiating the high power energy, okay,
yes sir.
If that energy, any device, whatever the device, drone or any device, they are working at a particular frequency. Okay, yes. Suppose drone is operating at 2.4 gigahertz, that is S band, and I am generating a high power microwave at 2.4 gigahertz. What will happen? That two frequency are matching now, that the frequency of the drone and frequency of my high power microwave.
Yes.
If these two frequency are matching, in that case, a very high current will flow in that drone circuit. If very high current will flow, since power is very high means very high current will flow. And if very high current will flow, what is the heat generated? I square RT, na?
Yes, sir.
If very high current is generated, what will happen? That circuit will burn out. In that way, we are able to neutralize the drones also, any electronic equipment. Means I can say this is a non-lethal device. Non-lethal device means it is not harming the human, but it is harming the enemy's electronic circuit.
Yes, sir.
Anything else?
No, sir. Thank you.
Any other students?
No, sir. No, sir.
No, students
evening,
from
sir.
the EC, that is your area.
Good evening, sir. I have a question.
Yes.
Yes.
Sir, what are the drawbacks of this that you have told us today?
Drawback is that for India, I can say the drawback is that we are not able to do much practical in the India, but in foreign we are, whatever I designed for the DRDO, this was only few organization is working on that device. Okay. In experimental, there is one drawback, and if you are going to other thing, that what drawback can be, but I am saying that drawback is only when there is sanction issue from the governments. Okay, but I think this drawback will not going to hamper much for our purpose. Okay, but
Okay, sir.
no, that is one more drawback is that we can't go beyond very I can say 12 or 14 gigahertz. One drawback is that. In that, what is happening? Just one in the slide, I have shown for S and X band. Okay, X band dimension is very small. Now you can see the X band dimension is very small. Okay, if we are moving to very high frequency, the dimension will be much small. In that case, fabrication or issue will occur. If we are designing also, we are able to design for a disk of very small size for high frequency, but what will happen, there will be minor change in the fabrication process also, because all these are designed with the that is high quality copper. Okay, if their dimension, there is a minor change also at high frequency, it will change the frequency, because the disk dimension is directly impacting the frequency of operation. Okay, at high frequency, it is we have to take much care, but at lower frequency, we need not to bother about that. Okay, but other devices like TWT, they people are working at high frequency, because they work with a different principle.
Okay, sir.
Anything else?
Yes, sir, many thanks. It was really a good session.
Thank you, sir. Thank you, sir.
Okay, Boyji, thank you for your valuable time for our students. My student is beneficial for your wonderful session.
Most welcome, sir.
Okay, thank you. I will talk to you later.
Okay, sir.
Okay, thank you, sir. Thank you.
Sir. Welcome, sir.
Well, thank you.
हेलो जुल्फिकार। जुल्फिकार, where are you? नहीं, मैम।